Hello, how are you doing?
Good. How you doing?
Good, thank you. Let's see if my headphone works here. Okay, so let's check out the lab. Okay, it does. Let me get caption real quick. All right. Give me 1 second. Sorry about this. So today we're going to do fast multiplication. And in the prior week, we did division and multiplication. So today we are going to look at how we can multiply with just shift add bits. Okay. And this is 8. So I'm aiming for you not to have homework by Sunday. And then I'll catch up with grading this week.
I appreciate that.
Yeah. Okay, let me make sure. I'm on the right screen here, sorry. All right. So let's talk about lab 8. In this week, we're gonna do multiplication with LC-3, but this time we're gonna look at how we can use the shift add bits instead of doing it like last week. You are gonna still have 2 inputs, and you're gonna have X and Y. So we would be able to test the value using the location. So when you look at the problem statement, you would know that this is where our value is going to be set. And your X is going to be at hex 3100, your Y is going to be at hex 3101, and your output is in the subsequent location. You are going to create a subroutine or a function called mult1, and we are going to do a shift add algorithm, and we'll talk a little bit about that. Okay, so that means that we have to fill for X and Y, and then we're going to fill for X, Y for the product. As far as the algorithm, we would know that, for example, if we have X is 13 decimal and Y is 43, when you multiply, when you do the multiplication, you would know that you would have a multiplicand and a multiplier, the top and the bottom. And as you know that binary value is only 0 and 1, so anytime that you multiply 1 by anything, it is itself. And anytime you multiply 0 with anything, it is 0 as an output. So when we look at the values here, for the first one on the right-hand side, for my multiplier, the least significant bit for it is a 1. So if you take 1, multiply it by the multiplicand, you get the multiplicand as the output. And then for the next value, you are going to shift and not add. So that means that you are still going to have the same thing, but because it is supposed to be all 0, you're not going to add it for the second value here as it is 0, right? So if I take 0 times 1, I get a 0. 0 times 1, I get a 0. So we're not going to add that. So we're going to treat it like nothing is there. So this is why you see that it is 0. We're going to shift left by 1 digit, just like how we multiply. but we're not going to add. Then on the next digit, which is the third digit from the right, which is a 1, we're going to take that 1 and we're going to multiply it by the multiplicand, which is going to be the same. But when we do that in multiplication, because it is a third digit, we're going to shift left, right? Again. So here you would see that it's we shifting 2 places and we put the same value. And then for the subsequent, which is also a 1, the last digit for the multiplier, we're going to take that and multiply it by the multiplicand, which is itself, what you see here. And when we got to that digit, because it is the fourth from the right, we're going to shift 3 places. And anytime that you have a 1 in a multiplier, you shift and add. Anytime you have a 0 in a multiplier, you shift but no add. Okay, so you need to visualize this as we go through the algorithm. So here it talks about what I just explained. We're going to start from the right to the left for the multiplier. If it is a 1, we're going to add and shift. And if it is a 0, we don't, right? So after the least significant bit on the multiplier, we're going to shift and add. If it is a 1 and 0, we're going to shift but no add. So we need to represent this in multiplication, and this is a different way that we would multiply. So we would see what the computer uses when it needs to multiply. And here it tells you that recall that in binary, multiplication by 2 is equivalent to a left shift, and that's very important. So when you multiply it by 2, you are going to do a left shift, right? Because it is the second digit, we are going to do a left shift, okay? Now, to implement this algorithm, we have to pay attention to the listing. This is how we're going to write it out. So this is our pseudocode. We need to compute product, which is P, and P represent X times Y. Y is the multiplicand, and X is the multiplier. Okay? So you would initialize P, you clear whatever register that would P represent or XY represent. And as you look at how these are, we simply are going to use a loop to represent each of the digits that we multiply. So that will be equivalent to the number of bits in the multiplier, which is X. So that means that we're going to have a for loop. And so we would say for I is 0, our first, we're going to start with the first index. And we're going to go to 14. And what we're going to do is we're going to implement the if, because the if is going to represent the condition for the value that would be a 1, right? We are going to shift and add. So if my multiplier digit is a 1, I'm going to shift and add. And so this is why you need to nest the if inside the for loop. Okay. And then notice that the comment here, it says that it's going to exclude the sign bit. So right now we're looking at just the positive value. And in the condition, if the value of X of I is 1, then our product is going to be a product plus Y. We add, right? We shift and we add. And in order to shift, just like when we learn when we did the sequence program, you simply do a reassignment here. So you're going to have Y is Y plus Y. And that is when you did your lab last week, we talked about how multiplication is really addition multiple times, right? So when you look at the y, which is the multiplicand, when I shift it for the one digit, which is the subsequent here, I simply shift it to the left. It is y plus y. Okay, this is a y and this is a y, right? That's your multiplicand. Okay, so y is going to be y plus y there. That's going to allow us to shift left. So in your LC3, it's going to look something like this to start. And so on the least significant bit, let's say that we're going to start with register 1. We're going to, let's say that that's a 0 or a 1. Then we can write the instruction like this. I clear register 2. I initialize register 2 at 1 because hex 1 represent that bit is turned on, right? This is going to be my multiplier. And then what I'm going to do is I'm going to take that, right, which is my register 2 now has 1. And my register 1 could be any value. I'm going to take that, I'm going to AND it. And I'm going to put it on register 0. At this point, what we can do is we can check to see if register 0 is a 0. And if it is, then it's going to branch. Because if it is a 0, right, we're going to send it to 0 because then your R1 is a 0. If it is not a 0, then it will do other things or it will go to the next line. Because anytime that you multiply it with a 0, then it is a 0, right? So this is why when you AND something with a 0, then its outcome is a 0. So it's going to check and register 0 for 0. And if it is, it's going to send it here. So what is the AND, the AND instruction about, right? It is a way that we can test the next bit for the shift. So as you can see here, that we note that the branch happens if that bit is a 0. If it is not, then it will just continue in the program. Now, in your assignment, it says you notice that by adding register 2 to itself, it's only going to add whatever the bit for the shift to the left by 1 position. So when you take R2, which is going to be the actual bit, you add it to itself, that's y plus y, right? This is what we see right here. Then it's going to be allowing us to do a left shift. Okay, so when you need to shift left, you're going to take whatever register that store y, we're going to add it to itself, and that's allowing us to be able to have the shift for y. Now for the function, which is our subroutine, we would start with the label molt1, right? And very similar to what you've seen last week, we also have to do the check with the sign. So we need to place the 1 for the sign. That's a bit that's going to hold the sign. And if x is less than 0, then we need to represent x as a negative. And then your sign is going to be a negative sign. So we need to convert it. If y is less than 0, then we need to represent y is negative y, and we need to sign y. And then our product is initialized, and we would have a do while. So this is from the earlier lab. So we would still have to implement something like this, but the majority of the algorithm is going to be with the shift and add bits. Okay, so this is the multiplication. So our task is to write the program. Don't forget to include how the subroutine is implemented in the program. So when we're done, you need to go back to Molt 1 and you need to explain that section of code. What is it doing? Okay. And then I need you to identify the system call and the services in the program. We talked about system calls. We talked about services and directives. What are the primary function of the system call and services? Identify the system call related to instructions, vector, and register. So if your program has like halt, right? What kind of vector is it using? Is it trap with the number? Or when you have some other pseudo operation, those are all system call related. And we already talked about this in the prior lecture. So this is the way for me to help you review what you learned in the past from our lecture. So think about the pseudo operation and the pseudo instruction that you use in the code, and you need to identify them and you need to think about what they're doing. Okay, and then you can set your values to be able to test. Okay, and I gave you the decimal here. You're welcome to convert it to hex and be able to, and you can use your calculator for that as well. Okay. And then answer the questions. What are the challenges you face in the program? How can you overcome the challenges? Right? Sometime, I know I already gave you the code, but if you have a hard time understanding, right, you need to make a note of that. And it's important to have that reflection because, you know, at some point you're going to have to know how to do your own LC3 program, right? So the whole point in this is to show you how we can implement solutions for something that's very simple, and you can use that for your project. All right, question. Okay, so let's go through the code now. And I had it written in Word, so that way it's a little bit easier to display for share screen. And when you look at the assignment, I think I already put in the screen capture of the code that I had, so you can use that and you can zoom in on it, so that way it's easy for you to see. So we start the program with the .org, which is our origination address, and it at hex 3000. Okay, and this is going to be where our program is going to begin. Then we're going to do a function call or jump to subroutine. And we're going to call function molt1, or we're going to jump to subroutine molt1, and we're going to halt. So simply, when you have functions, you need to call it where it's needed. And in this case, we built the whole entire function to multiply or add shift. In this program, you also see that I am using save and restore for register. Anytime that you're reusing, right, the values, you need to make sure that you save and restore, so that way the values stay intact and it doesn't get overwritten. So it's important to think about save and restore process in when you build a solution, especially for assembly. Right? So we would make a temporary location where we would put the value, and we would go back and retrieve that value for operation, for maybe our function and later output. So in the function, which is my subroutine, I have the label molt1 on the left, that because we jumped to the subroutine, so this is our subroutine. I start with storing each of the register to its appropriate label for save and restore. So My R0 is going to represent my X. My R1 is going to represent my Y. The reason why we have the other register store is we need to represent this as bits, not just numbers, right? So when you look at your assignment, you see that we use an example, the binary value multiplied by another binary value. These registers are going to hold the actual bit representation of the values. And then similar to the prior program, I am going to clear register 7 and initialize that. When you clear, that will be 0. So registers at 7 start with a 0 value. And then I want to add the 1 to it because that represents the sign, right? If you look at the pseudocode, the listing in yellow, it tells you that we need to find a way to indicate the sign, which is to add the 1. And I started with knowing that R0 or register 0 is going to be X and register 1 is going to be Y. So next part is going to load the label. So I'm going to load X to register 0. And then I clear. I'm sorry. I added, not clear. So I add register 0 to register 0. So at this point, R0 or X is 0. Now, if X is other things, then it is itself, right? When you add the 0. So if X is 0 and I add 0, it is going to be 0. If X is 1 and I add 0, then X is 1, a positive value. If X is -5, I add 0, register 0 will have -5. The reason why we need to do the add here is we're going to check for positive and negative, right? So coming back to what we talked about earlier, right here, we need to set this up so that way we can check for positive and negative value. So we did the sign, as you can see that we add the 1. And now what we're going to do is we have to check for X is positive and X is negative. So for the next part, here is where we're going to branch for 0 and positive. So whatever that you set the value for X before you run your program, it's going to place it on the register 0 after it has loaded. Then it's going to check for the value. So if I set my X is 10, then it's going to be a positive and it's going to go to the POS section. If I set my value for X is -4, right? It's going to, once it's loaded to register 0 and add 0 to it, it's going to be -4 right here. And it's not going to go to the POS section. So this is allowing us to do the if statement here. Branch to positive if positive number. And then now what we're going to do is we're going to test the sign. And earlier we add the 1 to start the sign, right? Remember that sign is negative sign. So at this point, we're going to add the -1 to register 7. Okay. So I'm doing this part right here. The step 5 for listing 5-4. So by adding the negative to register 7, right, which is going to be my sign, and store it back to register 7, I subtract 1 to test for the sign. And where I left off earlier, register 0 represent X. So I'm going to set up the 2 complement to indicate that it is -X. Okay, so we simply do the 1 complement there by doing not 0 and then add it with the 1 to have the 2's complement. So register 0 has negative x. Since we branch for POS or positive, we are going to define that now. So we need to load y to register 1. And similar to what you've done with x, you have to do the y here. So we're going to add 0 to the y and store it on register 1. So if y is a positive value, it's going to branch to POS2. If y is a negative value, right, it's going to use the sign, which is the next part. So we would take 0, add it with register 1, which is y, and put it on register 1. And it's going to use register 1 for the branching, which is the next line. So if register 1 is 0 or positive, it's going to send it to POS2. And then I subtract 1 from register 7 to test for sign, and then I would not complement. I would do the 2's complement, so the 1 complement and the 2's complement for y, which is negative y. Okay? Because in the case where if you have a negative times a negative, you can also have a positive, right? So this is why you also subtract it again. Any question? Okay, so we had earlier branched to POS2, so now we're going to have to define POS2. Now it really depends on developers. Some developer, they would keep it in a later section. I like to subsequently, once I handle that, I track my labels. So I want to make sure that if I had branch it, I gotta define it, and I normally do it right after because otherwise I'll forget. So for POS2, we are gonna clear register 4, 2, and 5. Now you can use other register here. You just gotta make sure that you track the register like what we talked about. So I just chose to use 2, 4, and 5. And for register 4, I used it as a counter. Okay, so this is going to allow me to count for the for loop. So what are we doing now, right? When you look at the pseudocode, coming back to top of page 2, you have this right here. Okay, you're getting ready to set up for the shift add. Okay. And why am I doing 15 instead of 14 like it says here? Remember that when you have the multiplier, it is a word. It goes from x of 0 to x of 15. So the 15 represent the nth bits in the x, right? From the least significant bit, which is bit 0 here, and the most significant bit, which is bit 15. So the nth of x, okay? Or the I of x, basically, based on this. So what you have is you need to set up the count for the bits, and that's going to be for register 4. So I simply take the decimal 15 and I add it to register 4, which I cleared, and I put it on register 4. So register 4 has the counter 15. And in the listing, it showed you that when you have a 1, you're going to add it and shift. So I can simply take the 1, and you can use hex or decimal here, but hex 1, add it with register 2, and put it on register 2. So register 2 has 1, and it's going to add 1 for the shift. Then I'm going to take my register 1, which is Y, and I'm going to copy it to register 6. The reason why I wanted to keep register 1 intact and do a copy is because I plan to reuse Y in register 1. If you modify register 1, you're going to end up having to reload it again. So you don't want that. If you load it to register 1, then you can copy it to another register for other operations. So here is where we do the copy. So R6 has Y. And now we're going to begin our loop. So I take register 2, which is the shift add bit, right? And I would add it to the Y. And when you look, right, it talks about your X is a multiplier, okay, and the Y is a multiplicand, right? So we want to work with the Y, and we need to loop for the X, because the X is this part right here, the Y is this part right here, okay? So this is why we would take that and we would take my R2, add it with my R6, which is Y, and then put it on register 3. So your register 3 is going to represent the most right-hand side bit, right? We start with the most right-hand side bit, which is your least significant bit. Okay, so that means that it is this one. So now in register 3, we're gonna check to see if it's 0. If it's 1, we're gonna add and then shift. If it's 0, we're just gonna shift, no add, right? So this is where you're gonna branch is 0. So it's gonna check the value for register 3 once it adds this. If it's a 0, it's gonna send it to the label is 0. And if it is not, right, it's gonna continue here. So we're going to do a branch to 0 and branch to the label is 0 if it is 0 as value. And then I'm going to take register 0, which is my X, and then I add it with my register 5 and put it on register 5, which is going to be my X value, my multiplier. Okay. We cleared register 5 earlier, so register 5 had nothing. We add it with X, so register 5 has X. And since we use is 0 to validate the least significant bit as a 0, we need to handle the shift. Okay. So you simply take it and add itself to be able to shift. So I would take register 2, add it with register 2, and put it back on register 2. That's allowing me to do a shift 1. Right? We don't add, we just shift. And then we would take X, which is in register 0, add it with itself, and put it on register 0, as we need to shift X. Okay, any question? Okay, so as we loop, right, we're gonna decrease. So remember that R4 was the count for the bit. So now we got 1 bit down, right? We're gonna subtract 1. And subtract 1 from R4, allowing us to check. If it is positive, we're going to keep looping. If it's not positive, when it gets to 0, it stops. Okay, so we decrease in our loop. Remember, R4 is our counter, so we count down. And so that will be positive for the loop. As long as it's positive, it's going to come back here, and it's going to do this, check for 0, and so on. Then for the next part, we're going to set up for when it is not 0, when it has a 1 for the multiplier. So I take whatever that value is and add it to 0 itself. It's going to be itself in register 7. So if I have a 1 in register 7, I add it with the 0, I get a 1, right? It is a positive. Or if I have a -1, it will be a negative, but here we would say not 0. So it's, if it's a 1, then it's going to go to not 0. Okay. And my product is in register 5, so I also need to handle it for the negative, right? Because if you have a positive times a negative, you have a negative. So you need to treat it with the product as well. So I need to complement that, right? So that would be the 1 complement here, add it with the 1. So my register 5 is 2 complemented. It represents the negative product as the output. And since we branch for not 0, we need to define it. So I store it to P. This is where I can see now, right? And then since I store register earlier, I gotta load it here. So load the save value from the register. So I'm gonna load it to the according label. Okay. So if you save register at the beginning, right, by storing, you gotta load it at the end. And so I did that for all 7 register, and I return for my function or my subroutine. So you do an RET. So one of the question in the lab was, what is the system call here, right? Remember that in your notes in your lecture, I talked about return and what happens in the return. So we return from the subroutine. Now for save register, when we use these labels, they're not like fully actual address. So I normally start with something like this. So I can track it x0, x1, x2, x3, x4, x5, x6, x7. Okay, so you still have to define those labels, but you don't use the normal address. Like in the 3000, you would use, by practice, you should use like the small value like this. And then I need to fill for my input to value x and y and my output so I can check. And then lastly, we have a .n. Okay. So the entire program is just a function basically. And the algorithm is to check to see if it's not 0. If it is 1, then we add and shift. If it is 0, then we just shift. And that's it. Any question? Okay, so let me get my simulator up. And then I already built my program. So after you write your program, make sure you save it as a .asm. Then you need to assemble it, right? And after you assemble it, you can load it to your simulator. If you're using the online one, you got to copy and paste your code on there. So we're going to load the program. Let me go to week 8. And before I run my program, I want to set X and Y, right? So I know that X is at hex 3100. Let's say that I'm going to use X is 2. And then the subsequent location, we can say 4, 2 times 4. So once you set X, Y, you're going to click OK. And then I run my program. Once I have ran my program, I simply just do a jump to. I have my values that's set and my output. Now, in this program, unlike your other programs, right, remember that we don't have overflow control. So when you test some of the values, you have to keep that in mind. In like other programs that we've done, we had overflow control. So you're able to have additional memory address to handle the larger values. But in this case, we didn't implement that. Okay, so as you can see, my program output. This is a fairly easy, simple program. So from here on out, the important things that you need to think about is, how you would be able to implement functions or subroutine. And in your subroutine, you have to think about the task, right, that addresses your overall objective of your program, ultimately procedure or algorithm that we want to implement. And as you are using values that could be modifiable throughout, we want to consider doing save and restore with the registers. And in this case, we did quite a few register. We did all of the registers because it represents the binary values, right? You want to give it space because sometime, like in the case where I have a hex 2, it's it should represent a byte, so that way you can have like numerical value that the ones and the 0 that's plugged in accordingly. Okay, so this represents 1 byte and to hold the binaries. All right, any question? Okay, so let's talk about some of the questions real quick. So I need you to take a look at Molt1, right? And it also helps when you look at this document. Earlier in the document, it shows you the listing, like the pseudocode, so you get a clearer picture of what you're really doing there. But look at the code for the function or the subroutine Molt1 and then tell me what it's doing there. And then for the system call and the services for the program. So throughout the program, you do see that we use system call. Okay. For example, like return, and then you have like pseudo instructions. Okay. So bring in those. And then for specific section, you can tell me what that system call is for. And then in addition to your, so you can use these two together, actually B and C for one. Okay. All right. Now, for testing the program, if that creates challenges, you can also note that, or overall, you're still trying to grasp it, you can also, I think a lot of my prior students, the hard part for them to understand was the add shift, right? So if you see this, then when you look at the algorithm, it's going to make more sense, right? Like we're checking for 0, 0, which is going to shift and not add. And when we shift, we take the Y value and add itself. Okay. All right. No question? Okay, so screenshot, answer the question. You can include it all in one lab document, upload it, submit it. You don't have any additional work. I actually took it off because originally I assigned homework assignment for this week, but it's spring break and I hope that you have some relaxing downtime and enjoy and just have some fun. And then when we come back, I will turn on the project. We'll talk about that. Okay. All right. Let's stop recording.